Today we're going to work on continuity and one-sided limits. So we'll be looking at how limits that we've been talking about will relate to knowing whether a function is continuous. And that will lead us to a discussion of looking at limits from just one side, either the left or the right, and how that affects a limit existing on both sides. So first of all, we'll start off with the definition of continuity at a point. And I would like for you to know the conditions that must be met for a function to be considered continuous. So the first statement is a function f is continuous at c. Remember, c is an x value if the following three conditions are met. Number one, the limit as x approaches c of f of x exists. So we must have it so that it is a limit that meets all the conditions of existing. And then two, that f of c is defined. And three, and maybe this one's the most important of all, that the limit as x approaches c of f of x has to equal f of c. So each one of those conditions must be met, and if so, then you may claim that a function is continuous at x equals c. Now, there are two types of discontinuities that we are going to look at. So this would be for functions that are not continuous. The two types of discontinuities we'll look at, first of all, are removable. And you can see that it says we can make the graph continuous by redefining f of c. And so graphically, that would look like a hole in the graph. And I have that illustrated for you to the right. If I were to color in this hole and take out the 0.31, then I could redefine my function at x equals 3, and therefore my function would be continuous. But since that is not the case, I do have a hole in the graph, then this is what we call a removable discontinuity. I can remove it by coloring in the hole, and therefore that's what gives it its name, removable discontinuity. Now, algebraically, you'll find removable discontinuities when you have, typically when you have a rational function, so a fraction function, and you have factors in the numerator and the denominator that cancel. So if you can take the numerator and denominator and cancel some common factor, then that's an indicator that you have a function with a removable discontinuity. So you have a picture of one, and then we'll have some problems where you can factor and cancel and see that happening. So I'm going to scroll on up and take a look at our other type of discontinuity, and that would be, mathematicians, maybe we're just not very verbal. So the opposite of removable would be non-removable. So a non-removable discontinuity would be if f could not be made continuous by redefining f of c. So I've given you a couple of graphs to look at below. The non-removable discontinuity is going to look like a separation in the graph. And this might be due to a vertical asymptote. And you see that in the graph on the left. This would be a picture where we have removable discontinuities at x equals -2 and at x equals 2 because the separation in the graph is caused by vertical asymptotes. Algebraically, you can have non-removable discontinuities in rational functions where after canceling, you still have factors that cause the denominator to equal 0. So once again, those fraction functions, after you're finished factoring and canceling, if there are still expressions in the denominator that would cause the denominator to equal 0, then you have a non-removable discontinuity in that function. You can also have non-removable discontinuities in piecewise functions. And I have a picture of a piecewise function for you to look at in the graph over here on the right. So you have a separation in the graph. It's caused by the fact that you have a function doing one thing as x approaches 2 from -1, from the left, and then something else as x is approaching -1 from the right. So those would be examples of non-removable discontinuities. And then your existence of a limit theorem is going to be based on something that I hope you've already discovered. We've tried to make this statement several times as we've been looking at limits, but now we're going to state it formally. And that is the limit as x approaches c of f of x equals L. It equals a certain number if and only if the limit as x approaches c from the left, remember I use a little negative sign to state that, of f of x equals the limit as x approaches c from the right of f of x. So that must be true for condition number 1 that I stated at the beginning to be the case. So the very first condition for continuity is that the limit has to exist. For a limit to exist, this has to be true, that from the left and from the right, as you approach a certain x value, those two limits have to equal the same number. We'll do a new video to move on to the backside of these notes.